How's it going, everybody? I hope you're having a great day. Let's see, we're going to look at how to find the surface area using double integrals of this particular example. So let's see what they're asking us. It says, find the surface area of the paraboloid. So they're already telling us it's a paraboloid. Z equals x squared plus y squared that lies under z equals 9. And so remember, this is just a plane where z equals 9. So let's see here. They're asking us for surface area, okay? So since they're asking you for surface area, remember that we're going to be asked to compute this double integral of a particular function where you get the partials and you square them, plus 1 dA, okay? So what we need, as we do with all double integrals, is we need to find the region, and then we want to consider the function that we're going to be using, okay? Here we have two equations with z's on them. But let's see, it most likely looks like this is going to be the function we're using. But there are no equations that have no z's on them. And so it's hard to see what this region is going to be. So this is probably one of those examples where you might kind of just want to have a good sketch to see what's going on. So let's see here. We have our x, y, z axis here. We're told it's a paraboloid. So just imagine that you wanted to find the traces for this here. If one of these is constant, then z will equal one of those variables squared, which is a parabola centered at the origin. And so most likely this will be a paraboloid centered at the origin. And then notice that if z is a constant, you just have a bunch of circles. And so it's going to be a nice little circular paraboloid going up like this. Okay? Let me wait to draw this piece here. And it's going to look like it's going to intersect the plane z equals 9. So if 9 is right here, and there's that plane that intersects it, it's going to intersect at a nice circle here, because notice, if you let z equal 9 where they intersect, this would be 9 here, and so that they're intersecting at this circle right here. And let's reread the question. It says, find the surface area of the paraboloid under this plane z equals 9. And so the paraboloid shoots up and it keeps going up forever, but they only want us to find the surface area of this bottom piece here, okay? The part that's underneath. So we need to see what is this. Remember that here you're trying to find the surface area of the surface of some function above some region D. So the question is, what is this region D? Well, imagine you cast a shadow of this paraboloid, only this piece that ends up here. If you cast a shadow on the bottom, notice that you're going to get this exact circle where these two intersect. And so you're going to get this nice little circle down here. And this circle down here is going to be that region D that we're talking about. And so notice that the surface is above the region D, and we want it to stop at this circle because after that we don't want to consider the rest of the surface. Okay? So the region D that we need to take a look at here on the xy plane is where these two are intersecting, and so z just becomes equal to 9. And so since you have that z is just equal to 9, you have, as we saw earlier, a nice little circle of radius 3. And so this little region D is just a nice little circle of radius 3. Let me make that a little better. Can I make that a little better here? Whatever, that's okay. So this is of radius 3 here, okay, of radius 3. And you can say, well, okay, now that I have my region D here, do I want to consider it in rectangular coordinates and do of type 1, where y is bounded below by some function and above, or of type 2? But as we've practiced in section 15.3, circles are a big indicator that we want to use polar coordinates, okay? Because notice, if we convert this in polar, this is just 3 equaling r, okay? So it's just r equals 3. And if we do that, that tells me that when I'm considering polar coordinates, I start from the origin, and no matter which angle I'm at, the smallest r can be is 0. Oh, damn, I didn't know it zoomed. Hey, that's lit. All right, anyway. You can start from the origin. Sorry, no, it just keeps going. And then the farthest r can stretch is up to the circle, the curve of the circle here, which is just where r equals 3, out here, okay? And so the smallest r can be, as it's stretching, is all the way to r equals 3, and the smallest it could be is 0. So then our bounds for r are the smallest it can be is 0, and the biggest it could be is 3. And then no matter what angle I'm going to be rotating at, I'm always on my region. So we're going to use 0 for theta all the way to pi. 2 pi, sorry. So theta will go from 0 all the way to 2 pi. Okay? Now, so we have our region. We have our region here. So when you're doing surface area, you want to figure out your region. But then, if you start constructing your bounds, what the heck is a function? Well, since we're looking at the surface of the paraboloid above this region D, we want to find a function for this surface, which is exactly here, because notice that even Z is isolated. And so this is a function we want to talk about. Okay? So the function of this surface is x squared plus y squared. So when you take the partial with respect to x, that's just 2x. When you take the partial with respect to y, that's just 2y. Okay? And so what we have is we want to look for this integral here, where the partials are these guys here. And so we're going to square them. So we get 2x squared for the partial with respect to x. 2x squared, that's just 4x squared. 4x squared plus 2y squared, which is just 4y squared plus 1 dA. Okay? So all I did is I just rewrote the actual function. We figured out that it's the paraboloid. We took the partials and we squared them. That's what we've done so far. Now that I found the function, now I want to figure out the bounds, and I want to convert. We're now going to convert into polar. Okay? And so I'm going to use the bounds that I found for r. R is bounded from 0 to 3, and theta is bounded from 0 to 2 pi. But now, notice that here I want to turn this into polar. And this, if I factor out the 4, that's just 4 times x squared plus y squared plus 1. And in polar, this is just 4r squared plus 1. Okay? So the inside is going to convert into polar, and it's going to be the square root of 4r squared plus 1. And then you look at this and you might be like, oh no, I might have to use trig substitution. But then you go, you know what? I remember from section 15.3 that dA pops out that r times dr d theta. And because now we have this r outside of my square root, if I integrate with respect to r, I know that I might be able to use this r somehow. And that's exactly what we're going to do. We're going to want to use u substitution. Okay, so let's see here. So we're going to use u substitution. Let u be the inside, 4r squared plus 1. So then we get du is equal to 8r dr. Okay, divide by 8. 1/8 du is equal to r dr, which is exactly this piece here. And so we're going to be able to distribute this 1/8. It's a constant, so I'm just going to take it all the way out. And so we get 1/8, and then theta goes from 0 to 2 pi, and then R goes from, well, again, so this is one of those problems where you can change the bounds for R if you want by plugging in the values here into U's, or you can take the antiderivative, convert it back to R. So I'm going to do that, okay? Take the antiderivative of this function here in terms of U, and then bring back the bounds. Actually, you know what? I just realized that in the future sections, we are going to want to practice changing these bounds. So let's just do that instead. Sorry. Okay. So when R equals 3, so I'm going to use this. When R equals 3, U is going to be 4 times 9. That's 36 plus 1. Okay. That's 37 for the upper bound. When R is 0, U is going to be 0 plus 1. So it's just U will be 1. Let me double check that. When R is 3, this will be 9 times 4, 36 plus 1. Yeah. Okay. So we're going to change this now into U going from 1 for the lower bound. And on top, it'll be 37. And then now we're going to rewrite everything in terms of U's. So the dr becomes 1/8 du, but the 1/8 I factored it out. And so in the inside, this is just the square root of U and then du. Okay? And then we have the d theta outside. But this is just right here, this is just u to the 1/2. So I could take the antiderivative of this. And then we get 1/8 integral from 0 to 2 pi. And then I get the antiderivative of this. I add 1. That's 3/2. So 2/3 u to the 3/2. And then now my new bounds are from 1 to 37 d theta. And so then I go ahead and I plug that in. And that root 37 is nasty. Okay, it is what it is. So let's see. So theta goes from 0 to 2 pi. And then let me just do this up here with you guys. So this will be 2/3, and I plug in the 37 to the 3/2. So that's 37 root 37. And then when I plug in the 1, that's just 2/3. Okay, so that's not too bad. So then we can factor out the 2/3. Okay? So, or here, let me not skip too many steps. So then we'll go, okay. So then the inside is 2/3 times 37 root 37 minus 1. Okay, all I did is I factored out the 2/3 from here. D theta. Oh, this is a big old constant. Yeah, I'm just noticing that right now. That's just a big old constant here. Okay, this is just big fat constant because there's no longer anything with thetas here since our bounds are just scalars. Woohoo! Okay, so we can just take this constant out and then multiply it with the 1/8. So this will reduce to 1 and this will reduce to a 4. So I get 1/12, 37 root 37 minus 1. Integral from theta going from 0 to 2 pi. Little Cartman came out there. And then we get 1/12. Whoops. 1/12. 37 root 37 minus 1. And then the integral of this is just going to be theta going from 0 to 2 pi. And that's just 2 pi. So then this will just be times 2 pi. And so then the 2's cancel off. This turns into a 6. Bam, beam, bada, boom. And so then we get pi over 6 times 37 root 37 minus 1. And that's going to be approximately, I think I wrote this down somewhere. There it is. 117.3 units squared, because remember you're doing the surface area of the paraboloid underneath the plane z equals 9. All right, guys? So the important pieces of this video is to keep in mind that you're not finding the volume of a solid underneath the surface of the region, right? You're finding surface area. And so usually the problems are not going to give you a specific, they're not going to give you an explicit function out in the open. So you might have to draw a quick sketch to get an understanding of what is the surface that they're talking about. Realize, hey, you know, this is the equation that z is either isolated, so I already have the function, or I might have to isolate z to get it so that I can find the function for z. And then the other important piece is what is the surface, what region is it above? Because in this case, we couldn't just, there was no equation without a z variable, right, as there usually is. So what we had to do in this case, see where the two surfaces intersected, and let z equal 9 here, and notice that I got a circle of radius 3. But then when you see circles for your regions, you're like, hell no, I'm not going to use rectangular coordinates, because that's going to give me, if you wanted to do that, you would have to isolate the y, and then y would be some positive square root function on the top, and then a negative square root function on the bottom. And then those would have been your bounds for y. But then you would have had to integrate this with respect to y and then plugged in those bounds. Bro, that would have been hella bad. So no, so we're going to do polar coordinates because it turned out to be easy. All right, folks, take care.